Good morning, students. Now, our last discussion in our last class was Ampere-Circuital law. Okay, Ampere-Circuital law already we have discussed, and its application in case of a long straight wire, solenoid and toroid has also been discussed. Today, I am starting today's lecture with an important question, an important board question of Ampere-Circuital law, which I have given you in the assignment, which I have uploaded yesterday. You can refer to the question number 14, question number 14 of this assignment. Look, this question says a straight, long, thick wire, it's thick wire, okay, of uniform cross section of radius A, okay, which is given by the bold line, that is the wire, okay, is carrying a steady current. It carries a steady current, capital I. The current is uniformly distributed across the cross section. In this cross section, the current is uniformly distributed. Mind this, it's a thick wire. Okay, what you have to do? Use Ampere-Circuital law to obtain relation showing the variation of magnetic field BR. They have written actually this as, here see, they have written as BR. R stands for, actually the variation of B is with R. What is R? I am coming to that point. BR inside and outside the wire. Okay, that means R will be the distance of the field point where we have to determine the magnetic field, the distance of that point from the center. Okay, and obviously that particular distance will be varying. Well, we have to find out R less than or equal to A, means inside and at the surface, and then greater than A. Okay, we have to show that this with the distance R is these two of the field point. You have got this assignment, so you have got this question, you can refer to it. Of the field point from the center of the cross section, what is the magnetic field at the surface of the wire? And you have to plot a graph showing the nature of the variation. Nature of the variation means inside and outside, how this magnetic field is varying. This is the first part. I am first talking about part A of this question. First, let us suppose what we do here, keeping this as the center and this distance as the radius. You look here, I can say this distance as A is the radius and this distance as R for the outside point. Let us say outside point. Let us say field point, outside point is P. Okay, I write here for outside point P, okay, R is greater than A. I am first finding out the field at the point P, outside point. I can say, I mark it 1. It is called an Amperian loop. Amperian loop is just like the Gaussian surface. Amperian loop is that loop in which we can apply Ampere-Circuital law. That is called the Amperian loop. So see, here it is. I remind you once again, our discussion was B vector dot dl vector integration along the closed loop, that is equal to mu naught I. Okay, this is the main form. Now what I do, I'm coming to this here. What happens? B is the magnetic field. Okay, B is the magnetic field at the point P, suppose here, and dot dl. So obviously we have discussed B and dl. In between B and dl, the angle will be 0 degree, because current is flowing like this, then around the wire. Okay, then we can write here in this, or better we once show B into dl into cos 0 is equal to mu naught I. I hope all of you understand why we have taken it 0. Okay, because dl vector and b vector will be in the same direction, and b is obviously at p we are finding out, and dl will be the total circumference. I write L is equal to mu naught I. It's very simple. BP is equal to mu naught I by twice pi r. Very simple, because L is what? It is the circumference of this Amperean loop, and what is this? Twice pi r, which implies BP is inversely proportional to r. Alright, BP is here. Look, BP is inversely proportional to r. We got the variation outside. Now, inside. If I take the point inside, let us say we consider an Amperean loop like this. Obviously, it is not very much geometrically, it will not be there. Here it is. Now, here, now I am considering this, look here. I am taking the Amperean loop inside. Suppose now I have to find out the field at the point Q. This is the Amperean loop 2. Okay, for inside point Q, that is r less than a. R less than a. Okay, we refer to the Amperean loop. Which one? 2. I take. For that, what we shall do? Obviously, now integration of b vector dot dl vector will be equal to mu naught into I dash. I dash means what? This I dash is the current contained in the Amperean loop inside. Okay? What is I dash is what? Current threaded by loop 2. Obviously, loop 2, less current it will thread. How to find out that current? First I find out the current density of wire. Obviously, wire is uniform, then how much will be the current density? I divided by obviously pi a square. You know, it is the current density. So I dash must be equal to I by pi a square. What is this? Current per unit area into the area r square. Mind this r I am keeping for inside point, because I told you r is varying. When we are taking outside point, this distance is r. When we are taking inside point, from center to the point Q is r. So that is equal to, this will be cancelled, I r square by a square. Here again according to Ampere's circuital law means from here what we are getting, BQ into here twice pi r as usual is equal to I r square by a square. That means from here one r will be cancelled. So how much will be BQ? BQ should be I into r divided by twice pi a square, which implies BQ is directly proportional to r. Look, the two variations we are getting, one is this for outside point, another is this for the inside point. Then this we have already found out. So what is the magnetic field at the surface? If I want to find out the magnetic field at the surface, so for field at the surface, okay, what will be there? R should be equal to A. You can use it in the first equation here, or any of the equation. You take here R is equal to A. If you take it, I think something is left here. Mu naught is left because mu naught I dash, so mu naught I dash. Okay, mu naught into this, so mu naught into this. Here, for this you find out BS surface. You take here only mu naught. For the R you can write A divided by twice pi A. Okay, how much you are twice pi A square? How much we are getting? You are getting mu naught by mu naught I. Mu naught I. Just a minute. I think something is missing. BS is equal to, from here we put R is equal to a mu naught I A by twice pi A square. This will be cancelled. Mu naught I by twice pi A. Look, this is the value of this field here at the surface. It's alright. Remaining portion, I am doing it. The remaining portion is here in the part A. Now you put here a graph BR. Okay, BR. Here this I write here distance from center. Center of what? Wire. That is R. It is R. The graph should be, look, it should be in this way. You just once check it. It goes like this. Here B is BP, I think BP is, or BQ is directly proportional to R. Here BP is inversely proportional to R. You just check it. R is equal to A. Look at this. Alright, this is the graph.